Radioactive decay. Let's do an example. A scientist has 244 grams of a radioactive substance. After 150 minutes, her sample has decayed to 30.5 grams. Part A, what is the half-life of the substance? So to get started on this problem, it's useful to know that we can model radioactive decay using the following equation. P of T is equal to P naught e to the KT, where P naught is the initial amount of the substance, and K is the decay rate. Now, the decay rate is basically just a constant that tells you how steep your exponential function is. So it's a constant, and it's always negative because this is an exponential function that's kind of like going down over time. Okay, so you want to have this equation handy when you're working with radioactive decay. And we also need to know what the half-life is. So the half-life, by definition, is the amount of time it takes for the substance to decay to half of its original amount. Okay. So let's take a look at the information that we're given and try to figure out how to find the half-life of this substance. So we're told that the scientist starts out with 244 grams of whatever radioactive substance this is. So that means we actually are given P naught here. So we know that P naught is equal to 244 grams for this problem. We are not told the decay rate, but we are told that after 150 minutes, the substance decays to 30.5 grams. So it decays quite a bit after 150 minutes. Now, we have this general equation for the decay rate of a radioactive substance. We know what P naught is. We don't know what K is. But we do know something about what the output P of T is, or like how much substance there is after a certain number of minutes. And this extra little bit of information right here about how after 150 minutes the sample decays to 30.5 grams, that'll actually allow us to find K. So we can like find K with that extra info. And it's useful to find K because if we know what K is, and we know what P naught is, we have our equation that models the decay of this radioactive substance. And if we have an equation to model it, we're going to be able to figure out how much time it takes for the substance to decay to its original, or sorry, for it to decay by half. And in other words, if we know this equation, we can find the half-life. So I'm going to do this problem in the following way. I'm going to first find K. So I'm going to first find K, and then second, I'm going to use the equation P of T equals P naught e to the KT, where we know what K is and P naught is, to find the half-life. So that's going to be my strategy. Okay, so we have this general equation for the decay of a radioactive substance, P naught e to the KT. And we know that P naught is equal to 244. We were given that. We also know that after 150 minutes, the sample decays to 30.5 grams. So after 150 mins, sample decays to 30.5 grams. Now, mathematically, if we were to write this in equation form, that would be the following. P of t is equal to 30.5 when t equals 150. Or substituting this into our equation here, we have the output for this function, or 30.5, is equal to P naught e to the k times 150. So when I put 150 minutes in for this time spot, I'm supposed to get 30.5 as an output. Now we know P naught, so I can substitute that in here. So we know 30.5 has to be equal to 244 e to the 150 k. I'm just changing the order of the 150 and the k because it's the convention to put the constant in front of the variable. Okay, this is really great because now we have an equation with just one unknown in it. So if you have an equation with just one unknown like this, just a k here, we can actually solve for it. And we can use our strategies for solving exponential equations to do this. So how do I solve for k? I'm going to isolate the exponential function first. So what do I mean by that? I'm going to get the e to the 150k by itself on one side by dividing both sides by 244. So if I do divided by 244 divided by 244, I end up getting 30.5 over 244 equals e to the 150k. Now, why would I want to isolate this exponential function e to the 150k? Because I can actually get rid of this base e now by taking the natural log of both sides of this. So I can do ln of 30.5 over 244 equals ln of e to the 150k. And the reason I isolated the exponential function is because right here, ln of e to the 150, so ln of e to the 150k, those cancel away if the e is just by itself, if there's nothing in front of it. So I can cancel right here, and now I have solved the right-hand side for 150k. So I'm almost there. All I have to do now is divide both sides by 150. And if I divide both sides by 150, I've solved for k. It's pretty complicated looking, but we have an exact form for it. Okay, so it's a little bit complicated looking. So at this point, what I'm going to do is I'm going to type this into my calculator and round it. So this is our decay rate. It's a constant. So if we type this into the calculator, we will get k is approximately negative 0.013863. So I'm keeping a lot of numbers after here, and that's because we're going to use this again. And anytime you want to use a rounded number again in an equation, it's good to keep a lot of the numbers after the decimal. Otherwise, you might end up with a rounding error when you enter your answer into an online homework set. So I'm keeping quite a few numbers here. And notice we got a negative. So for these radioactive decay problems, you should always get your k is negative. And if you don't, you need to look into your work and find where your mistake is. Okay, so we're partway there. Remember, our goal is to find the half-life. So our goal is to find the half-life. Remember, goal, find the half-life. Okay, now we know that our general equation for the decay of this substance is P naught e to the kt. And we actually know what P naught is. Remember, it's 244. And now we know what K is, and that's going to be really useful. Here's why. We want to know the amount of time it takes for the substance to decay to half of the original amount. So the original amount is 244. So 244 is the original amount. One half of original amount is going to be 1/2 of 244. In other words, it is 122 grams. So if we want to know what the half-life is, so to find the half-life, what we can do is we can figure out the amount of time, or the T, when the output here is 122. So we can figure out the time you would have to plug in order for the output of this function to be 122, 1/2 of the original amount. So if I solve, if I solve the following equation for T, so if I solve 122 equals 244 e to the negative 0.013863t. If I solve this for t, the t that I find is the half-life. So the t that you plug in here, and so that the output for this function is 1/2 of the original amount, that's by definition half-life. So we're going to take this equation and solve for t now. If I divide both sides by 244, I get 122 over 244 equals this. And that gives us 1/2 on the left. And now I can do my trick where I take natural log of both sides. So I do ln of 1/2 and ln of e to this k value, t. And now on the right, ln and e are inverse functions, so these cancel each other out. And we get the following. And we can divide both sides by that k value to solve for t. So I'm going to divide on the right by negative 0.013863 and on the left by that same value. So that these cancel away and we get t. So t is equal to the following. Okay. Now, we want to type this into a calculator because this doesn't really tell us anything about how many minutes it is. If you look at that, you don't have a sense of how many minutes it takes for the substance to decay to half its original amount. So if you type this into the calculator, you're going to get 117. That is not true. You're going to get t is equal to 50. So actually it ends up being an exact number. So let's change this to exact. Okay, so that is our answer to part A. What does this answer represent? It's in minutes. So it takes 50 minutes for the substance to decay to half its original amount. Okay, let's do part B. So part B is how much of the substance is left after 53 minutes. So part B is a little bit shorter. We have our equation that models the decay of the substance. We know it's 244 e to the negative 0.013863t. And we're just being asked, after 53 minutes, or when t is equal to 53, how much substance is there? So P of t is some amount of substance in grams. So all we have to do for part B is plug 53 minutes in for t. And if we plug that into our calculator and round, we get 117.03, and this is measured in grams. We know that from earlier.